Hi everyone, welcome to this presentation about this paper called SemRoDe, Macro-Adversarial Training to Learn Representation that are Robust to Adversarial Attacks. This is being done in collaboration with NUS, A*STAR, and NTU. These are some of the collaborators. So adversarial attacks on text, they still work. And in our particular paper, we focus on word-level substitutions. And what this means, to give you an example, is that if we take BERT that was set up as a sentiment classifier, we can change a word in an input to maybe a synonym. Now, to us, this change would result in being the same sentiment as before, but to the model, it creates a misclassification. And we say that this is an attack. There are multiple ways to define a threat model for language attacks. In our particular work, we focus on a grey box scenario where we assume that the attacker has access to the output logits, but it does not have access to things like the model weights or the input embedding space, and hence can only carry out his attacks at the token level by performing word substitutions. There currently is multiple techniques that try to do adversarial training on text, which follow a adversarial training formulation, which means that they have a min-max operation where they introduce a delta within your input ets, and this perturbation is bounded by an epsilon. And this epsilon, more often than not, is set to an L2 ball with fixed radius, potentially a hyperrectangle, or even a convex hull. To give you an example, if we take a normal model that was trained on sentiment classification for movie reviews, for example BERT, an attacker will achieve roughly a 13% accuracy under attack of the model if he attacks with text footer. Now, a defender can use these white box adversarial training techniques and improve the performance marginally, maybe up to 20%. But naturally, this is not as good as we would like this robustness to be. Now, we'll show in our work that we can actually increase this to even 40% on this particular dataset. And we believe that the performance is not as good as it could be because the attack components of these adversarial training techniques, which operate at the input embedding space, are fundamentally different to the attacks that attackers use, which is predominantly by changing tokens, adding tokens, or doing word substitutions. And by introducing these adversarial perturbations within the input embedding space, you create two main problems. The first problem is that the input embedding perturbations lead to meaningless embeddings, which cannot be mapped back to the input token space, and therefore there's no one-to-one mapping. And secondly, word-level attacks lead to very large and also kind of unexpected differences in the high-level features, especially if you compare these distances to the original samples. Hence, we will first focus on the first problem, which is the meaningless embeddings. So why is this a problem? We can take this as an example. If we have an L2 ball of fixed radius, which again is in the input embedding space and doesn't have any meaning or linguistic characteristics to it, if we then take an input embedding such as already and we add a delta, this delta will add some numbers to this vector, and the resulting vector will not be equivalent to a vector which is an actual word, right? This vector will maximize the loss at the output given your objective function, but yeah, it's not going to represent anything meaningful, and it's going to be bounded by this L2 objective. Now, this is a meaningless embedding, but also if you were to then take this yellow dot, which is your meaningless embedding, and you were to find the nearest actual word embedding substitution, what you'll see is that with a large enough delta, the substitutions are actually also quite bad and do not fit the context. So for example, already would change to something like strong if you're using FreeLB with enough delta perturbations or a delta that is large enough. And the second point is that once you've trained using this L2 ball, then the attacker doesn't have access to the input embeddings. They will perturb the input tokens. For example, if you change the word ranking to rank, it actually may turn out that this word substitution is completely out of bounds, and therefore it can still attack your defended model. There are some techniques that attempt to improve the performance on word substitution attacks by, for example, introducing the convex hull, but this is highly dependent on the dictionary that you're going to be using to perform these word substitutions in the embedding space. And the issue with this is that then the attacker can come along and then basically just use his own set or a different set of word substitutions for each word. And what this might introduce is word substitutions that your adversarial training technique did not see yet, and therefore still attack your model. So for example, you might train on glove embeddings, but then the attacker uses WordNet. Now, going into the second main problem is that we introduce unexpected high-level feature differences in the output feature space. What this means is that if we take, for example, this is a good day, which is a non-perturbed sample, this will be projected into something that we call a base domain. But then if we perturb this sample and we do inference with this perturbed sample, it will be projected into an adversarial domain. And this is something that we do not want. We believe these large differences are predominantly due to the fact that when you do word substitutions, the delta is very, very large. So for example, if we take good and we substitute it with fine, you basically have a delta which is substitution dependent. And if you look at the actual embedding, like the numbers, the delta that you add for each value is very, very large. So in this work, we have three main contributions. The first one is that we do show indeed that adversarial samples and normal samples belong to two different distributions in a feature space, which we believe belong to two different domains. Secondly, that if we add a regularizer between these two distributions and we train to align these features, then the model will learn to project both base and adversarial samples to a new robust domain, and that increases the robustness. And lastly, we show that we can train on one set of word substitutions, but it generalizes well enough to other word substitution sets. So we're looking to basically align these two domains, and the way that we implement it is with a LDist regularizer, and we test multiple feature alignment techniques such as MMD, Coral, and optimal transport. And then we show that once we have this robust domain, the model is more robust to adversarial attacks. This is basically how we formulate it. So we have, for the original accuracy, an objective which would follow, for example, if you're doing classification, either binary or cross-entropy loss. But then we have an operation here, which is our LDist, and we believe that as you add word substitution perturbations, such as G, X plus delta, within a bound, which we will describe later, this will basically increase the distance between your original base domain and the adversarial domain. And naturally, we want to then minimize this distance as it's becoming larger. And yeah, once we minimize this, we expect a more robust model. We assume that adversarial samples are on-manifold and have high quality features. And for epsilon, we use a semantic similarity encoder to make sure that the original sample and the adversarial sample are very, very similar in terms of meaning. And one thing that we find is that as we are training, the distance between the base features and the adversarial features becomes lower, and we believe that this shows the alignment happening. And once it converges, we see that it leads to more aligned distributions in a feature space. Now, it's very hard to show this on a 2D plot, but we believe that in a higher dimensional space, let's say 1,000 features, we will actually see the adversarial domain and the base domain to kind of like converge towards one robust domain. And the model starts projecting all samples onto this robust domain. And what we see is, firstly, that the attacker, now that is trying to attack and perturb a sample, needs to perturb more words to achieve the same attack. So for example, previously on the non-robust model, it only needs 2 adversarial word substitutions to achieve a successful perturbation from 0 to 1. But now it needs 5 word substitutions to achieve the same result. Then we show that MMD is kind of like the most stable training technique. We also kind of see that optimal transport works quite well, but it's very difficult to find the right set of hyperparameters. And thirdly, as we can see here, although we train and then test on Tetzfuller, we also show that if we train on Tetzfuller, but then we attack using different dictionaries, for example, contextual, which is BERT attack, or WordNet substitutions, our performance holds. So for future work, we would like to test fine-grained conditional alignment. So for example, what happens if LDIS is between class 0 from the base domain and class 0 of the adversarial domain? We want to see if our defense techniques is also robust against other types of adversarial samples. And also we want to do more analysis on the distributions. So in conclusion, we showed that the base and adversarial samples belong in 2 different distributions in language, and that if you align the features in these distributions, it increases robust generalization, especially to word level attacks. Thank you so much for listening. Bye.